Okay, so all our discussions so far about DSP systems has revolved around ideal systems. And the block diagram of ideal systems will just ignore the anti-aliasing filter for the time being. The block diagram has always been, okay, we have an input signal, we pass it through a continuous to discrete block with some scaling time t. We have an impulse response, we have a discrete time system hn. The output of that is taken and then passed through a discrete to continuous block, and we get yr of t. Now, a practical system has many issues that we have ignored, for example, in this continuous to discrete block and in this discrete to continuous block. And it is important for us to at least be aware of these issues and understand some of the basic terminologies and concepts. So a practical system sampling block will look like the following. First of all, the chances that your input signal will really be band limited are going to be really low. So you will almost always be using an anti-aliasing filter. Now the challenge here will be that even in this case of anti-aliasing filter, this is not going to be an ideal low-pass filter. Instead of this filter, and what we mean by that is that an ideal low-pass filter, we have talked about an anti-aliasing filter is going to be this perfect box with a cutoff of pi by t and minus pi by t. In reality, most filters will stay close to 1, but they will not be perfectly sort of 1, and they can't have, the most important thing is they can't have this sharp decay from 1 to 0. So most filters have what is called a roll-off. Even if they go 1, they roll off slowly. Okay? So they have a roll-off, and there is no sharp boundary of these filters. So this is what a practical system will look like. You can make the roll-off sharper and sharper, but that requires more and more expensive hardware. So that is one of the basic concepts, that if you want to make a sharp filter, because anti-aliasing filter is a continuous time filter, you are implementing it in continuous time. Okay? So that's one practicality that you should be aware of. Now, let's go after that. When you go to G tilde A of t, the question is, how is this continuous to discrete block implemented in practice? We have said that you sample it, and your samples, for example, we say Gn. The ideal case is Gn are simply going to be equal to G tilde A of nt. Well, in reality, this is not going to be the case. In reality, you typically have, how you implement that varies, but at the very least, you have a block which is called sample and hold. Yeah. So this is called sample and hold circuit. And then you have a block which is called an analog to digital converter. And then you get back this G tilde n, which is not perfectly this G of n. Okay. Now, in many commercial systems, the ADC and the sample and hold circuitry are actually packaged in one chip. So, and you still call that an ADC. So let's talk about what is this sample and hold thing. Okay. So let's take the example that, say, G tilde of A of t is this signal. Let's take the example of a sinusoidal type of signal, doesn't matter what it is. So this is your input signal. Ideal sampling says, ideally when we sample it, we say, well, you will start sampling at, let's, without loss of generality, say this is t equal to 0, this is t equal to capital T, t equal to 2t. So you will store this value, you will store this value, you will store the next t equal to 3t value, and so forth. But how do you measure these values? In a hardware, no matter what physical hardware you use, it has some finite processing time. It needs some finite amount of time before what's called the settling time, before all the circuits can settle down and produce an output. So what the sample and hold circuit does is actually, say you want to sample, sample this point, this second point, t equal to t. Well, that value needs to stay constant at the input of some circuitry so that the circuitry can read that value properly. So the purpose of sample and hold is that it samples this value and then it holds that value for some time t. It keeps the value constant for that time. Okay, and so it samples and it holds it, and this time, the hold time is a function of what's called the settling time of the ADC. Okay. There is no ADC which can instantaneously measure an input. So these values could be in microseconds, they could be in nanoseconds, but it's not going to be 0. So that's the sample and hold. Now in reality, when it is doing the sample and hold, when it is doing this holding, the signal has been changing during that time. And the way it implements, actually, instead of keeping the value constant at that particular value, most sample and hold circuits actually generate a value which is an average of whatever was the signal doing during this period. So if your signal, I'll blow this part up. So if your signal was going like this, you wanted to sample here, the sample and hold circuitry will actually end up producing some average value which will be around this point during this phase. So we'll sweep under the rug the details of the hardware implementation. We'll just say that sample and hold, when it does that, you're not going to get the exact sample value at that point. Okay. So that is one aspect of the practical DSP systems. And that is because ADC systems need some settling time before they can produce an output. If you read the output of the ADC during this settling time, you'll get garbage. Now we'll get back to the discussion of ADC. We'll return to it again. Let's now talk about so this was for the case we are saying the continuous to discrete block can be expanded in this fashion. Now let's talk about the discrete to continuous block. So let's talk about a practical reconstruction block. So ideally we say we have a discrete input, we pass it through discrete to continuous time converter, and we get back a continuous time signal. Now again, this block can be expanded into, you have, so if the output is a sequence yn and the continuous time is yrt, in reality, what are called DACs or digital to analog converters, they get back a sequence and then they have something called a zero order hold circuit. So this is a circuit which basically takes your sequence value and generates a staircase output. And after that, you have to have what's called a compensation reconstruction filter. And then you produce the output y hat r of t, which is close to y r of t, but there are going to be some imperfections in there. So let's talk about what does the zero order hold circuit look like. So zero order hold circuit or it's also called the staircase reconstruction. So in an ideal setting, what we talked about was, let's say you are given these samples, these discrete time samples, and let's say this is y of 0, y of 1, y of 2, y of 3. And we talked about, if you go back to how we derived the discrete to continuous time block, we said you first convert it to impulses. So you go from here to, so this is discrete time, 0, 1, 2. There's no notion of time. You go from this to continuous time where you have impulses, and the area of each impulse is proportional to your signal value. So this is at time t equal to 0. At time t equal to 1, to capital T, you generate another impulse, y1, and so forth. Now in a hardware, you can't generate these impulses. Direct deltas are idealizations. If you remember how direct deltas are derived, it's a limiting case of signals which are just contracting and rising in height. You can't generate these impulses in continuous time. In discrete time, an impulse is a perfectly valid signal. In continuous time, an impulse is a mathematical construction. You can come close to it on hardware, but you can never generate an impulse. So what happens in continuous time is, instead what you do is what's called the zero order hold circuit, which is that you actually take this sequence, every value, and you generate an output which stays constant for t seconds. So you basically say, I'll take y0, so a zero order hold circuit, it will basically take y0, whatever the value of y0 is, and it will hold that for capital T seconds. So this value will be y of 0. This is now in continuous time. So this is t equal to 0. At t equal to capital T, it will go to the next value, which is y1, and it will hold that for t seconds. At next t seconds, it will go to y2 and hold that for t seconds. So this is now y1. This is y2. Okay. And then it again goes up and holds at y3. So it's like a staircase. You are making a staircase out of your input signal or of your discrete time sequence. Okay. And of course, you can see that t gets smaller and smaller and smaller. It's just like the integration that you do, that you are getting these staircases, which is going to look more and more like your input signal. Okay. So instead of the ideal reconstruction, which involves the sinc interpolation, you can see that this is sort of interpolation, but now using just this constant signal value. Okay. You can also write that down. So actually, you can also derive that. So if you remember your sinc interpolation formula, the sinc interpolation, or just the reconstruction formula, the reconstruction formula is n from minus infinity to infinity, y of n, hr of t minus nt. Where hr is the impulse response of your reconstruction filter. Now in ideal reconstruction, this hr is, now in this case, actually, you can also derive this entire thing where you say that your ideal reconstruction filter has been replaced by a reconstruction filter whose impulse response hz of t is given by this constant value, which is, it is from 0 to t, it takes the value 1. Okay. So this is the reconstruction filter for the zero order hold circuit. Okay. Where hz, I'm writing z instead of hrt to say that this is for the zero order hold circuit. So this entire thing actually can be written as summation of n from minus infinity to infinity yn hz of t minus nt. Because all you are doing is you are taking your sample and you are multiplying it with this constant pulse with height 1, so its height will become yn, and then it stays there for t seconds. Okay. So instead of sinc interpolation, now you are doing interpolation with this pulse. And what is the impulse response of this filter? hz of j omega. So the Fourier transform of this zero order hold circuit is a sinc in time by the duality principle, sine of omega t by 2 by omega by 2. And since we are delaying it, it's not symmetric around 0. There is a phase shift, which is e to the minus j capital omega t by 2. Okay. So the point of this discussion is that this zero order hold circuit can effectively be thought of as a reconstruction filter, but now your reconstruction filter, instead of this ideal reconstruction filter minus pi by t to pi by t, okay, and height of t, you are actually looking at a reconstruction filter I'm just going to do the plot, the magnitude plot, hz of j omega absolute value. You have a reconstruction filter which looks like this. It's still sort of like a low pass filter, but it's not a perfect low pass filter. So to compensate for this staircase, what you end up is, so because we don't have the ideal reconstruction filter, we cannot guarantee that the output here at this point is not going to be the output here in the ideal case. So to compensate for this, what happens is in a digital to analog converter or DACs, they often implement what's called a compensation reconstruction filter, which tries to invert the effects of this non-ideal reconstruction filter or the zero order Hall circuit. So there's often a compensation filter which is ideally given by h hat r j omega, which is given by what you wanted, the ideal reconstruction filter. So this is the ideal frequency response divided by hz of j omega. Okay. And its expression ends up being omega t by 2 over sine of omega t by 2 e to the j omega t by 2 for omega less than or equal to omega c and 0 otherwise. Okay. So the idea is they're just trying to invert the effects of this non-ideal reconstruction filter so that together with this compensation filter, this whole block, the hope is that the non-ideal reconstruction filter and the compensation filter should behave approximately as an ideal reconstruction filter. Now that is not going to happen in general, but you try to come as close to it as you can. Okay? So that's the other aspect, that in real DSP systems, again, I'm not interested in going into too much details, but it's important for you to realize that all the continuous to discrete and discrete to continuous blocks that we have been talking about, in reality, they have many imperfections. And this staircase reconstruction, this week's lab, will help you get some understanding of that also. Okay. So we have discussed about the imperfections in the sample and hold circuitry. In the reconstruction side, we have talked about the zero order hold circuit and the compensation reconstruction filter. The last point that we need to discuss is what are the imperfections caused by an ADC. Okay. So even if we ignore all the imperfections in our sampling system, one of the things that the sampling theory assumes is that ideally, if you sample your signal Gn every time t, then you get GNT. Right? So right now I'm ignoring all the previous imperfections that we had talked about. So if this is your signal, right? If you sample it here, then this is the value you will record. If you sample it here, this is the value you will record, and so forth. If the amplitude of the signal was higher, then you will record higher values, and technically this mathematical formulation doesn't care what the value of Gn is. It just records that value. Now, in practice, these sampling systems are made up of circuits, and they cannot actually record infinite values. So they have a certain range within which they get to record signal values. Okay? So the first practical consideration of using ADCs that ADCs can only detect values between some maximum, let's call it eta max, and some minimum, let's call it eta min. So if the value of the signal goes above, if Gn is bigger than eta max, then ADC goes in what's called the saturation mode, in the sense that even though Gn is bigger than eta max, the ADC cannot record bigger than eta max. Okay, so that is called, the phenomenon is called clipping. Okay. And the same if Gn is less than eta min. Okay. Same thing happens. So to give you a visual, again, ignoring all the other aspects of imperfections, let's say that this is what your input signal was, and your ADC had a maximum, this was its eta max, and this was its eta min. Okay. So up to this point, the ADC will record everything as it is, but once it gets to this point, which is in the range where the signal value has gone above the maximum, the ADC will saturate. It will just record this value, the maximum, that's it. Similarly here, here, and then it will return back to its normal operation when it is within the range. When again it goes below the eta min limit, then it will just record this value. Okay. So if you look at ADC data sheets, they actually limit, okay, the maximum value of ADC is this, the minimum value of ADC is this. And the difference between the maximum and the minimum, eta max minus eta min, let's call it R, this is called the dynamic range of an ADC. Now in general, people just talk about the dynamic range more than what is the absolute value of eta max and eta min. They will say the dynamic range of this ADC is 2 volts, which means from the maximum and the minimum, it records, and anything which is within 2 volts, it records it. Okay, so this is what we know about ADCs in terms of the dynamic range. They can't do they can't just take any value, maximum, minimum. They have a finite dynamic range. Now there is another issue with ADCs, which is not so much an issue with the ADCs, but the fact that when you are doing digital systems, whatever value you record, So when we measure Gn, which is G of nt, at the end of the day, we want to store it inside a computer or some sort of a digital system. It is stored in some digital system. So what happens is that even when the input falls within the dynamic range, even when G of n is within the dynamic range of the ADC, actually what the ADC generates is only an approximation to that Gn. It does not generate the exact Gn. And the reason for that is because since ADCs have a finite number of bits, or equivalently you can say since the system that you are using has only a finite number of bits, what we store is different than Gn. Okay. So when you go and read the data sheet of an ADC, it will say it's a 16-bit ADC, it's a 24-bit ADC, it's a 32-bit ADC. In general, an ADC is specified by a certain number of bits say B. Okay. And if an ADC has B bits, then it can only store a certain number of values. So if an ADC is B bits, then it can only store or generate, since ADCs don't really store values, but they generate and then you store them in some digital system, they can only store 2 to the B unique values or generate 2 to the B unique values. Okay? And this B is called resolution of the ADC. So the number of values generated by a B-bit ADC, let's call it n, is of course 2 to the B. Okay. Now here is then the challenge. Again, go back to our picture that we drew earlier. This is your input signal. Now again, we'll just focus on the aspect of finite number of bits. Forget about dynamic range and any other errors. So this is the signal range. Let's focus on this, right? From 0 to, let's call it V max. The signal takes from 0 to V max. How many numbers exist between 0 and V max? So originally, your signal can take any possible number of values, the total number of values that exist between 0 and V max or any other range. There are infinite values. For a continuous time signal, if you are doing a digital signal which only was taking plus 5 volts, minus 5 volts, then that's different. So technically, when I sample my signal, Gn, original Gn, when I write Gn, that's the true Gn, can take infinite number of values. But here is the challenge. My ADC can only generate n values, where n equals to 2b. So then what do we do? What we will have to do is map many of the values onto a single number. Okay, we'll have to divide this infinite number of values into chunks so that there are only 2 to the b chunks of values available to us, and then we map them. And how do we do that? We basically divide this range in vertically, right? We divide the values vertically and we say that anything that falls under this chunk will be assigned a value somewhere in the middle. Okay, so this process is called quantization, an extremely important topic when you are doing sampling. Quantization is the process by which you say that how to convert all possible values between the maximum and minimum range of the ADC, between eta min and eta max, into 2 to the b numbers. If you want to think about a motivation for this, gradings in universities which use letter grades is a good example. So theoretically speaking, let's say if you have 0 to 100%, a student could take any number between 0 and 100%. Some students will take 80%, some will take 81%, some will take 85%. But the instructor only has the ability to give certain number of letter grades. Say A, B plus B, C plus C, D, F, 7 grades. So effectively, the instructor is asked to divide the 0 to 100 scale into 7 chunks. And what happens if someone falls in one of the ranges of that chunk? That person is assigned a grade. So multiple students with different values, someone has 90, someone has 95, they get assigned to the same grade. At the end of the day, all you are given is grade, and you can't really tell whether a student had higher marks or lower marks if they have the same grade. Quantization is similar kind of a process, but in the context of ADCs. Now, there are many different forms of quantization. I want you to be aware of that, but the most simpler quantization form, and that most, at least consumer grade ADCs implement, is called uniform quantization. So what is uniform quantization? You have a range. So your dynamic range is R. You divide it equally into 2 to the B pieces, and then assign Gn to the middle of the piece. Okay. So it is like saying let's say if I had only 5 letter grades, I take 0 to 100, divide it equally into 5 pieces. So 0 to 20 is F, 20 to 40 is next grade, 40 to 60 is next grade, and so forth. Okay. It's similar kind of a process. So in this diagram that I showed earlier, uniform quantization will be that you will actually divide it equally into pieces, this vertical axis. And so if any value were to fall between this and this, I will actually assign it 0 value. Any value were to fall in this next bin, I will assign it the middle value, whatever is the value there. So of course, what is the size of each bin, or what is the size of each quantization? The term that is used is quantization interval. So that simple math, your ADC has a total range of R, and you have a total of 2 to the B numbers. So you divide it into R divided by 2 to the B. That's little delta, or some people write it capital delta. That's your quantization interval, or quantization bin size, quantization level, whatever you want to call it. Yeah. So one picture that this is a picture we have divided explicitly the y-axis into pieces. Right? So let's do it a little bit more carefully. Okay, let's say that this is your 0. Okay. And what I do is, so this is my now y-axis. And I'm going to divide it into bins. And typically, when people talk about quantization, because we already talked about it, that if you are given a signal, you can always offset it. So what really matters is the range. So for this discussion, let's assume that the signal is basically sort of symmetric around 0 value. So the first bin, it's traditional to make the first bin around 0, so that the first value that gets assigned is to 0 if you fall in that region. So you have intervals of size delta. So here is, for example, one interval. Right? So this is the size of this interval is delta. Now, if I sample if I sample at this point, so these are all the values that are between that range. So if I were to, mathematically speaking, sample something here, this is my value. My value is not 0. But because I have a quantizer, I have an ADC, when it measures any value in this range, it's going to assign that value 0. So if I actually go and look at what is the value that my ADC is producing at this point, the ADC will produce this 0 value instead of non-zero value. There will, of course, be another interval. So the next interval will be, again, of size delta from this point to this point. And if any value of Gn originally falls, so in here, everything gets assigned to 0. In here, the next value that will be assigned will be the middle of the next interval. Now, what will be the value of the middle of that next interval? If my interval is delta, right, then it's delta by 2 is the 1/2. So what I have is this part is delta by 2, and this part is delta by 2 also. So this next value that I get assigned is actually delta. Okay. So I have one value which is 0. The next value that I assign is delta. Okay. Again, if any, now I take a sample. Let's say I take a sample here. This is my original value, but what will happen is the location will not change, but what will happen is that my quantizer will actually record this value, delta value. Okay. Again, I will have, so let's say, let's do the example with 4 levels, which means that you have a 2-bit ADC. So for the third level, there is another, let's assume that this is the next level. So again, it will assign the value in the middle of that level, and that value will be 3 delta by 2. Oh, sorry, 2 delta. This number will be 3 delta by 2, and this will be 5 delta by 2. Okay, so again, the same principle. You take a sample. Let's say you took a sample at this point. Right? This was your value. And what your ADC will do is it actually will record this value, which is the 2 delta number. Okay? Similarly, you will have a next block here. So this number will be minus delta. And if you were to take a sample that fell in anywhere in this range, let's say you take a sample, it is here. Okay. What your ADC will record is, regardless of the value of the sample at this point, it will record this time it will record a higher value than the truth. Okay. So what happens is that when you're using an ADC, actual value is G of n, but ADC produces, due to quantization, you can write it as Q of Gn equal to G hat n, okay? Which in most cases is not going to be equal to Gn. Now, what is the maximum error between the truth and what the ADC records? What can be the maximum error? The maximum error will be that, so let's focus on this region, right? This is a region of size delta. Now, the maximum error will be that you are very close to this endpoint, but you recorded delta by 2. Okay? Because if you are around here, anywhere closer to delta by 2, your error is going to be smaller. Right? So the maximum quantization error that is defined as the absolute difference between your quantized value and your truth, that is going to be delta by 2. Okay. So how can you make this? So one of the lessons of this discussion is that actually digital systems lose information in multiple ways. And one of the basic ways that they lose information is because of this quantization. What you measure is not exactly what the signal had because you had to quantize it to a certain number of values. But this quantization error can, of course, be reduced. So how do you reduce the quantization error? The quantization error is given by delta over 2, which is the function of your quantization interval. And the quantization interval delta is a function of, so it's a function of the number of bits. And so the more number of bits you have, the smaller this delta is. So while you may incur a large error for a 4-bit ADC, you go to 16-bit ADC, the error becomes pretty non-negligible. It becomes comparable to the other noise in your system. You go to 32-bit ADC and you may not even care. So it's that message that you should just keep in mind. There are imperfections, there are approximations involved in digital systems. But as you go to higher number of bits, those approximations become more and more realistic. It is still important to be aware of these aspects.